I want to talk about how to find the biggest and smallest values of continuous functions with regards to closed intervals. There's lots of reasons why you might be interested in the biggest and smallest values of functions. For example, imagine you had a function that modeled the amount of money your company made as a function of certain decisions. I think you could see why you'd be interested in maximizing a profit function. On the other hand, let's say you had a function that modeled the danger to your person for a specific situation as a function of different decisions you could make. So I think you could see why in that case you would be very interested in finding the minimum of that danger function. Okay? I'm going to be focusing on continuous functions and closed intervals for my discussion of finding the biggest and smallest values. The reason is because for that specific situation, we are guaranteed to have a biggest and smallest value. Why? Because of the extreme value theorem. Go back and read up on what that guaranteed. Okay? You're not always guaranteed to have a biggest and smallest value, but for a closed interval and a continuous function, you will have a biggest and smallest value. All right? So now, let's start talking about how you find the biggest and smallest values for continuous functions and closed interval. All right? So first, the good news is to understand that we don't need to consider all infinite points on the closed interval. Okay? That's because the biggest and smallest values can only occur at what are called critical points. Okay? So the next question is, well, what is a critical point? Okay? Critical points are either endpoints or points where the derivative is 0 or undefined. Okay? Now, let me show you some examples to make this more concrete. Okay? I'm going to draw 3 segments of different continuous functions, and each example is going to, the extrema are going to occur at different types of critical points. All right? So here's an example where the biggest and smallest values occur at the endpoints of a segment of a continuous function. What about a linear function? Okay? Can you see that the biggest and smallest values occur at the endpoints? Okay? For the next case, think about the sine function. What does a sine function look like? Okay, here's a piece of a sine function, and the biggest and smallest values occur at the top of the little mountain-shaped part and then the bottom of the little valley-shaped part. And at those points, the derivatives are 0. If you have trouble seeing why that's the case, remember that the derivative is the slope of the tangent line at a point. And so what does a tangent line look like at the top of the mountain and the bottom of the valley? It's horizontal. Okay? Horizontal lines have slopes of 0. Okay? For the example of extrema where the derivative is undefined, think about a point that had corners. A graph that looked like the following. Okay? Now, at a corner, the derivative is undefined because the derivative limit does not exist. If you try to take the limit, you'd get a different value from both directions. Okay? Another way of seeing it is that the slope on either side is different. Okay? And clearly there the maximum and the minimum are occurring at corners. Okay, where the derivative is undefined. All right, another example where you have an extremum where the derivative is undefined. Think about the absolute value function, right? It's V-shaped. Okay, at the bottom of the V, the slope is undefined. That's a minimum. Okay, another example where the derivative is 0. Think about a parabola, a quadratic. Okay, y equals x squared, for example. that has a minimum at the origin. That's the derivative is 0 there. Okay? Let's do another example of something you might see on a homework or an AP exam. Okay? So suppose you needed to find the biggest and smallest values of this function for this closed interval. All right? So our plan is going to be we're going to find the critical points and then compare the function values at those critical points. Okay? So let's first get the x values of the critical points. Okay, so clearly the endpoints are in. Okay, and then we're not going to have for this polynomial, for any polynomial, we're not going to have a situation where the derivative is undefined. So the only other type of critical point is going to be where the derivative is 0. The derivative of this function is 12x squared minus 12x cubed. Let's set that equal to 0. Divide by 12. Okay, don't divide by x squared or you'll lose a critical point. However, if you factor out the x squared, now we can see that x is either 0 or 1. So let's add 0 and 1 to our collection of x values of critical points. All right, those are the only x values where the biggest and smallest values can occur. All right, so now let's find the function values at those x values. So f of minus 1 is minus 4 minus 3. F of 2 is 4 times 2 cubed minus 3 times 2 to the 4. That's 32 minus 48 is minus 16. F of 0 is 0. F of 1 is 4 minus 3, which is 1. Okay, so clearly the maximum occurs at the point 1, 1, and the minimum occurs at the point 2, minus 16 on the graph. Okay, so feel free to watch this more than once, but that's a great example to show you how to calculate the biggest and smallest values of a continuous function on a closed interval. Okay, now the last thing I want to talk about is I want to discuss the fact that sometimes people don't want the absolute biggest or smallest value, but they might also be interested in the biggest or smallest value for little subintervals. Okay? So let's talk about that next. So imagine you were interested in a function that had the following graph. Okay, so just by inspection you can see where the biggest and smallest values occur. I'll put a blue dot there. Okay, so those are the absolute biggest and smallest values. Okay, so let me go ahead and label them. So the one of them is the absolute maximum. Okay, and the other one is the absolute minimum. Okay, now on the other hand, can you see that you have a smaller mountain and a shallower valley? And so let me put a purple dot at the top of the smaller mountain and a purple dot at the bottom of the smaller valley, the shallower valley, or whatever you call it. Okay, now those are not the absolute biggest and smallest values. However, for a subinterval, for a little interval that includes one or both of those points, they are the max and min. Okay, now we can't call them the absolute max and min. However, they for a little local region, they're the max and min. Okay, so for that reason, we're going to label those the local maximum, and we'll label the other one the local minimum. Okay, So those are still the tops of mountains or the bottoms of valleys, and they still can only occur at critical points. Okay, so that's an important point to remember. So you can't find the local extrema by comparing the function values. Okay, that's how you find the absolute extrema. Okay, now so to explain how to find the local extrema, I want you to notice that the slope is a different sign on both sides of the local extrema. Okay, for the local maximum, the top of the mountain, notice that the derivative is positive on the left side and negative on the right side. That's going to be how you're going to tell if it's a local maximum. On the other hand, for the local minimum, notice that the derivative is negative on the left side and positive on the right side. Okay? For your information, analyzing the signs of the derivatives on both sides of a critical point, that's called the first derivative test. Okay, that if you have a critical point and the sign changes sign, and the derivative changes sign as you move across the critical point in a certain way, then it's a local extremum. All right. Now let me do an example that will make all of this hopefully much more clear. And again, you can revisit this example I'm about to do many times if you'd like. It hopefully will explain a lot, make a lot of things clear. So let's close with this example. Suppose that we wanted to find the absolute extrema and the local extrema for this function. And it's going to be a piecewise function. Minus, this function is g of x is minus x squared minus 2x plus 2 for x is less than or equal to 0, and x squared minus 2x plus 2 for x is greater than 0. And we want to focus on the closed interval minus 4 comma 4. Okay? By the way, another name for local extrema is relative extrema. You'll sometimes in the literature see people talking about relative maxima and relative minima. Okay, that's the same thing as a local maxima and local minima, FYI. All right, so let's see if we could find the absolute and local extrema for this example. So the x values of the closed intervals, let's find that first. X values of the critical points. Okay, so the endpoints, minus 4 and 4, those are the easiest to find. And then for the other critical points, we're going to have to find the derivative. So g prime of x is equal to minus 2x minus 2 for x is less than 0, and 2x minus 2 for x is greater than 0. Okay, and if you at 0, if you take the limit as x approaches 0 from both directions, you get minus 2. So either one of those pieces you can include x equals 0, doesn't matter. All right, so now if we set the derivative, if we set each of those two pieces of g prime equal to 0, go ahead and do that, and you will see that you will get x equal to 1 and minus 1. All right, so 1 and minus 1 are going to be added to our critical point x value collection. Okay? Now, to wrap up the absolute extrema, let's find the function values for all of those points. Okay? So g of 4 is equal to 16 minus 8 plus 2, which is 10. G of minus 4 is minus 16 plus 8 plus 2, which is minus 6. G of 1 is 1 minus 2 plus 2, which is 1. G of minus 1 is minus 1 plus 2 plus 2 is 3. All right, so now it should be obvious that the absolute max occurs at the point 4 comma 10. The absolute minimum occurs at the point -4 comma -6. Okay? Now let's finish by doing the local extrema. And remember, to do that, we're going to use what's called the first derivative test. I'm going to analyze the derivative on both sides of each of the remaining critical points. All right? So the remaining critical points are the 1 and the -1. Okay? So let's draw the piece at the bottom of the whiteboard. Let's draw a piece of the x-axis that we are focusing on. And the interval goes from -4 to 4. Okay? And we have a critical point at 1 and -1. Okay, so critical point at x equal to -4, x equal to -1, x equal to 1, and x equal to 4. All right. Actually, we're okay. So the endpoints are the absolute extrema. So we're only caring right now about the x equals 1 and x equals -1 points, because we're looking for the local extrema now. Okay. So for the region, for the interval for x between -4 and -1, go ahead and pick any value in that region and plug it into the g prime function. For example, -2. Okay, if you plug that in, you will get 2 for the derivative. So in this region, the derivative is positive. Okay, now between the -1 and the 1, you can pick any value. 0 is a good choice. Okay, and there, plug into the g, so g prime of 0, you'll get a negative value. So in this region, the derivative is negative. Okay, and then in the final region, for x values between 1 and 4, maybe pick x equal to 2, and then you can see that so g prime of 2 is positive, so in this region, the slope will be positive. Okay, so if you were to imagine what a positive slope and a negative slope looks like, I hope you can see that x equal -1 is the top of a mountain, and x equal to 1 is the bottom of a valley. Okay, so a local minimum occurs at 1 comma 1, and a local max occurs at -1 comma 3.